So, voltage. Uh, Voltage is so voltage alternative names. Sometimes it's called electric potential difference. Sometimes it's known as electric pressure. Um, because whenever you read a question and it says, "What is the electric pressure?" I mean, why do we call speed and velocity different things? They do have a slightly different meaning, but okay, let me ask you this: why do we have words that are synonyms? Why don't we just remove all the synonyms and just have one word? So the reason why there are different names is because you can think of voltage as a pressure, and these terms are used a lot. For example, a lot of questions will ask you to solve for the electric potential difference. So the reason why it's sometimes called this is because you can think of voltage as being potential energy. In which case, if you are solving an energy question, a lot of time you want to think in terms of potentials and kinetic. In which case, you would be describing voltage as electric potential difference. Sometimes it's just electric potential. So this is more descriptive in the terms of potential energies, because you're saying what is the potential due to electricity. So this would literally mean what is the potential in the context of only electric. Um, because when you get into electromagnetics, you could have a potential due to the magnetic potential, or you could have a potential due to the electric potential. That's actually probably the better thing, because when you start learning about electromagnetics, like electromagnetics, sometimes you need to figure out what the potential is from the magnetic potential and what the potential is from the electric portion. Mm-hmm. And knowing that the potential due to electric is the same thing as voltage, you can immediately replace electric potential with the word voltage. And we have Ohm's law, and we have other laws that allow you to solve for voltage. So knowing that this word means voltage allows you to simplify a whole lot of equations. Um, we also have a voltage drop. You can think of a battery as being a source of voltage and resistors as being consumers of voltage. Thus, as you go across a resistor, the voltage is reduced. At least in series. So what I mean by that is, let's look at this circuit right here. Let's suppose I hook up a 12 volt battery and I have a 6 ohm resistor and another 6 ohm resistor. What is this circuit equivalent to? So this is equivalent to a circuit that is connected to a single 12 ohm resistor. And what is the current coming out of this circuit? So current is equal to voltage over resistance, where voltage is 12 volts, our resistance is 12 ohms, so we have 1 ohm and 1 amp. So 1 amp is coming out of the circuit. Now this circuit is the same as this circuit. So we have 1 ohm coming out of this circuit. If we were to look at, and this would be the positive side, and this would be the negative side. If we were to look at only this resistor, we know that because these two are in series, this 1 amp of current is going to flow down this resistor, and 1 amp of current is going to flow down this resistor. We can reapply Ohm's law. So voltage is equal to current times resistance. So the current is 1 amp. The resistance is 6 ohms. And so the voltage across this resistor is 6 volts. And this would be the positive side, and this would be the negative side here. Yes. Yes. Keep your mask on, Thomas. We can do the same thing with this one. The voltage would be equal to current times resistance. And it's the same values. Should have chose different values to really illustrate this. This is also 6 volts. And it'd be positive, negative. So if we were to go around a circle around this around this loop, the battery gives us 12 volts, but this resistor is going to consume 6 volts. This resistor is going to consume 6 volts, and we end up with all the voltage used by the time we get back here. A lot of time in circuit diagrams, they will indicate that one side is providing 12 volts and one side is producing 0 volts. And we can see that as we step down, we go from 12 volts on the positive terminal, and the negative terminal of the battery is 0 volts. So this is another reason electric potential difference is used, is that we compare the voltage at 2 different points. We usually would put the voltage up here as being 12 volts, and the voltage down here as being 0 volts. So this would be equivalent to writing the circuit like this. Ohms. Another way you could have done it is, you might have seen the symbol. Anyone ever seen the symbol? no, that's a battery. So this is a battery. This is also a battery. But this symbol is ground. And ground is, we usually let ground be 0 volts, our common voltage. So if we started with 12 volts being supplied to one side of the circuit, the resistors will eventually consume all the voltage until we reach the other side and reach 0 volts. Keep your mask on, Thomas. So let's do a more complicated circuit. So let's have 10 volts here. Let's have 5 ohms here. And let's let this be 20 ohms. And this be 20 ohms. Like this. Yes. Oh, so the only thing that matters, so I could hook this circuit up. It doesn't make any difference. I could hook this circuit up to where one terminal is connected to 1,010 volts, and the other end of it equal to 1,000,000 volts, and it would make no difference. And keep your mask on, Thomas. It makes no difference. This circuit would work the exact same. Only the difference in voltages matter. I could have connected this up to negative 20 volts on one side and negative 10 volts on the other side, and it would work the exact same. This is plus 10 volts compared to this terminal. But anyway, let's say we wanted to find the voltage and current of everything in the circuit. So the first thing is we need to find the total current. So these two are in parallel and can be replaced with a single resistor. So 1/1/20 plus 1/20 is equal to 10 ohms. And these two are now in series and can be replaced with a single resistor, which is 15 ohms. And we can find out the total current leaving here. So current is equal to voltage over resistance. And so we end up with 10 volts over 15 ohms. And that gives us 2/3, right? So the current leaving this battery is 0.667 amps. I said ohms earlier, I meant amps. So let's say that we want to now figure out what the current and voltage is across everything in the original circuit. So this right here corresponds to this portion of the original circuit. So let's find the voltage drops. We know that the the current going through this resistor right here will be the same because this is connected in series with the battery. Series means same current, so the current going through this resistor is 2/3 of an amp. And we can solve for the voltage across that resistor. Voltage is going to be equal to current times resistance. So that would be equal to 0.667 amps times the resistance of 5 ohms. Which gives us that cross. So this is plus minus. So this would be plus minus here. This would be plus minus here. And so we get a value of 3.33 carried. So 3.333 carried volts. And so the voltage across this resistor is 3.3 volts. And the voltage across this resistor, you should already know it would be just 10 minus 3.33 because it has to be, I should say that the one thing to note is the voltage around any loop, regardless of the loop, sums to 0. And if we go from, so if we're going around the circuit and we encounter the minus sign first and the plus of a resistor, we consider the voltage positive. And if we go in the opposite, if we encounter a plus first and then a minus, we consider the voltage negative. In doing this math, only in doing this math. Yeah. So coming back here, we can see the voltage drop across this will be I times R. The current is going to continue going down because it's in series. So remember that in series, current doesn't change. And so the current is 0.667 amps. The resistance is 10 ohms. And so we get the voltage drop across here to be 6.667 volts. Now this was equivalent to this. So the voltage drop from this point right here and this point right here, the voltage drop between these 2 points is 6.667 volts. Remember that in parallel components have same voltage. Now, we know that the current going down this resistor is 6.667 amps. Some of the current is going to go down to the left, and some of the current is going to go down to the right. To calculate how much current goes to the left and how much current goes to the right, we simply apply Ohm's law. The current down the left is going to be equal to the voltage drop divided by the left resistor's value. We saw that the voltage drop is 6.667 volts, and that the resistor's left value is 20 ohms. And so the current down the left branch is just equal to 0.333 amps. Since these are the same values, I know that they're going to be the same for both. So on the left side, we're going to have 0.333 amps. And down the right side, we're going to have 0.333 amps. So the general technique for completely solving circuits, the reason why I had you do all that, is to first find the total resistance, and that can get you the total current. And once you work down, and one of the reasons why you want to redraw the circuit every single time, is then once you go down to one resistor, you work your way back up. We can find the voltage drop across this component, and that's going to correspond to the voltage drop across these two resistors. We can also find the current entering through here, which will give us the current coming down here. Thomas, wake up and keep your mask on. Lift your head up. Lift your head up, Thomas. Alright. Static electricity. If I can spell, I'm going to bring both. Is simply an accumulation of excess charge. If you have a sharp point like this, so if you have, imagine a metal fork with a very sharp point, or the tip of a knife blade. There are atoms, and atoms have protons that are positive, and you have electrons circling around them. What ends up happening is negative charges end up collecting toward the tip or edges of materials. The electrons like to collect on sharp points. Which would be more dangerous? Putting a steel ball, sphere, so a ball bearing, into a microwave, or putting a fork into a microwave? Why? But why does it spark? It actually has to do with the shape of the fork. If you put a fork versus a spoon in the microwave and the spoon was very dull, having dull edges, you might not even notice any sparks. However, if you put a fork in the microwave, it's almost guaranteed to produce a lot of arcs. This is the reason why aluminum foil in a microwave is very dangerous. Usually when you put aluminum foil, you crinkle it up and it creates these sharp edges all over the place. And keep your mask on. These sharp points allow electrons to collect on them and arc off. Now, what would happen if I took something like rubber and run a sharp point over it? Let's say it's dull enough that it doesn't cut. Now, what would happen is these electrons will eventually go up inside this. Because this is conductive, the electrons are going to want to collect on the points. And what can happen is we can build up a difference of charges. As you might remember, this is known as, does anyone remember a device that does this? Van de Graaff generator. Before I do that, I want to pull up something. So let's build that circuit we designed a second ago. So let's put a battery. Connect the wires up. Then we're going to have two resistors down here. So battery, I said was 10 volts. Resistor, first resistor, I said was 5 ohms. These two, I said were 20 ohms. Note the electron flow. So replacing this with a battery. So this is the positive side. Which way is the electron flowing out of the battery? They're coming out of the negative side. So the electrons flow in opposite of the current. Remember that the conventional current is opposite to the actual flow of electrons. So the current we always put coming out the positive side, but the electron flow is the opposite. So if I were to measure the voltage, so put the negative terminal of a voltmeter to here, we measure 10 volts. And if I come over here and put it like this, I get 3.33 volts, which is what I calculated earlier. And if I come over here and measure like this, I get 6.67 volts. And note, if we were to flip these around, it would read negative, so it does matter. And if I come over here and measure current, the current leaving this was 2/3 of an amp. And we see it branches across the left resistor with 1/3 of an amp, and across the right with 1/3. If I were to change this value, make that 10, we see more current is able to go across the right and the left, and the total current changed.